Hello friends, welcome to this video, and in this video we are going to perform the task of object localization and the classification. So let us revise the concept of object detection. It is a technique used in computer vision to identify and locate object within an image or a video. It can be used for a wide range of applications such as object counting, tracking, and localization. Now what are the objectives of this video? So, first of all, we are going to build a simple object detector using a pre-trained mobile net version 2 in the TensorFlow framework. And after that, we are going to use it to perform the localization and the classification task. Here you can see an example of a car. Okay? Here you can see the blue box which represents the ground truth and the red box which represent the predicted. And here you can also see the IOU score, so which is really good, that is 84% of IOU. And here you can see both the classes, the ground truth class and the predicted class. So this is what our prediction at the end of this video would look like. Now let us understand a bit about the data set which we are going to use for this video tutorial. The name of the data set is Stanford Car Detection Dataset, and it contain 196 classes which are really huge for a simple object detection task. But still we're going to prefer this data set as it is really simple in nature, and here it provide both training and testing. And you can see both training and testing contain more than 8,000 images. Next, it provides you with the bounding box and also the class label or the class index. Okay, the format of bounding box is like x1, y1, then x2 and y2. Here x1 and y1 represent the top left of the bounding box. If you can imagine a bounding box here, the top left would be x1 and y1, the bottom right would be x2, y2. Now let's take a look at the dataset itself. Here you can see the folder and the files which are found in the dataset. You can check the description to download the dataset. First of all, let's take a look at the CSV file. So here you can see we have 6 columns in this file. So first is the name of the file, then it has 4 columns for the bounding box point, that is x1, y1, x2, y2, and the last column represents the class index. So here the value of class index or the class label is from 1 to 196, but when we write the code during training, we're gonna subtract it by 1 because our class index would begin from 0 instead of 1. So just remember this point. Next we have annotation train.csv, which is basically same as the test, just this is for training and the previous one is for testing. Here also we follow the same format. Name of the image x1, y1, x2, y2 and the class label. Now we have another file, that is names.csv. If you see, both these contain indexes, so we don't know the real name, and this file contains the real name, that is the class labels. So this car belongs to the index number 1 and 2 and 3, so like this it contains 196 rows, each representing a class. Okay, so these are the files which we have. Next we are going to take a look at the images which are inside this car underscore data folder. So here you can see we have test and the train folder, and inside each the test and the train folder we have 196 sub folders, each representing a class, and within each class folder we have sample for that class. So here each folder contain near about 42 samples, I believe, just a mean number. It can go up to like 45, 42, 40, in some cases it can go down to 40 or even 28 in some cases I have seen. So it's a kind of imbalanced data set, but still fine for our need. Okay, so now let's move back to our slides. So now we're going to talk about the architecture or the method which we're going to use in this video. So We are going to use a pre-trained MobileNet version 2 because our need is to build a simple, lightweight and easy to train architecture. First advantage is that it is pre-trained, so maybe we can skip the training of the MobileNet version 2. We can just directly train the rest of the layer. Let's go about this block diagram. So this is our input image. It is fed to the pre-trained MobileNet version 2. After that, we take the output from this network, this pre-trained network, and pass it via a conv 2D. That is, it's a one by one convolution layer. Then it follows a batch normalization, ReLU activation function. After that, it is followed by a global average pooling layer. Next, we have a dropout to improve the efficiency of the performance. Next, we have two branches. So first one is for the bounding box regression, and second is for classification. So this is the dense layer which is followed by the sigmoid. It gives you four values, that is x1, y1, x2, y2. The second dense layer followed by softmax give you class probabilities. Okay, now let's try to implement this architecture in the TensorFlow. Okay, so first of all, we are going to import all the layers, not the layer, the functionalities and libraries which we require. Okay, so we have imported all the layers basically as L, that we're going to use this L to import all the, to call all the layer. Then we have this model class which we require at the end when our output is, we have our outputs. And the third is the MobileNet version 2, which we're going to use as a pre-trained architecture, or you can say the backbone. So let's begin with our function called build model. Is going to take an input shape, then number of classes, because here we are going to do two tasks, bounding box regression and the classification. So by default, num classes would be equal to 196. Next, we're going to have our inputs layer. So we're going to say inputs L dot input, then input shape. So this is our input layer. Next, we're going to call our backbone. So backbone would be equal to MobileNet version 2. Now here, because we are only interested in the CNN part of this MobileNet, that is the feature extracted part. So we're gonna say include top to false. So include top equals to false basically refers that we don't want the classifier part, just remove that. Okay, next we have weights. These weights are from the ImageNet, which makes this model more efficient in terms of training. So because of that, it will require less data. Now we're going to give input to it in the form of input tensor. Next, a alpha value, which is basically a width multiplier, 0.1. So now we have our backbone. So let's print its summary. Let me just have this main function here, this main line from where the execution began. So we need an input shape first. Let's say for now 256 by 320. I've just after seeing the images, I find this would be the approximate size which would fit all the images. Okay, now we're going to call our build model function, give it the input shape. Number of classes by default is 196. We don't need to change. Now let's run this program. Okay, I haven't activated my environment for the TensorFlow. So I have two different environment, one for TensorFlow, one for PyTorch, so I don't mix them. Okay, here you can see this is the pre-trained backbone, that is MobileNet version 2. If we go up, you can see the inputs shape, that is 256 by 320. Okay, now we're gonna extract this output from there. If we go back to slide, you can see we extract this output and pass through these layers. Okay, so let's comment it out. Let's say this is the detection head. Okay, so let's say x equals to backbone dot output. This is one simple way. So with this way you get the last output. But if you want any specific layer, let's say, let me go up, any activation function, yeah, just say you want this as your output. So what you can do, you can say simply, let me comment it out, x equals to name of the network, that is backbone. You can say get layer, name of the layer and output. This would also work. Okay, with this you get the specific layer output, but with this you get the output of the last layer. So I want the output of the last layer, then it is followed by a one by one conv layer. Number of output channel would be 256, kernel size would be 1, padding would be same, x as the input. Now it would be followed by a batch normalization. Next, the ReLU activation, which is one of the mostly used activation function. I think recently people are trying to use GILU, another activation function, mostly because of its introduction with the transformers. You can also try that. If it works for you, it's fine, no issue. Next, after activation function, we have global average pooling layer. X as the input. Now if let's go back to our diagram. Okay, after gap we need a dropout, and after that we have these two different branches. Okay, so let me add dropout here, 0.5. Now two output, first would be our b box, then it's gonna output 4 value, x1, x2, y1, y2. Activation is ReLU, not ReLU, sigmoid. So what sigmoid does is it gives a value in the range of 0 and 1. Let's give it a name and call it b box, x as the input. Next would be label, that is the classification layer, dense. Now its output number of feature would be number of classes, because we want is probability over class. Activation is softmax. Let's give it a name and call it label, x as the input. So we have our input here, we have our output here. Now let's build the model class. So we're going to say inputs equals to inputs, then outputs equals to b box and label. Okay, so we're going to give this back the model. Let's give a value here. Now we're going to say model dot summary. Okay, so our architecture part is done. Let's run this and see. Okay, we have something. Okay, so it's now working. So if I see, so till above this layer and above is the pre-trained mobile net version 2. After that, here we have layers which are built from scratch. Okay, here you can see it began with 256, then it has batch normalization, ReLU activation, global average pooling, then we have dropout and 2 layers as the outputs. This part is going to be trained from scratch, so you have like 2 strategies in which you can train. Either you can train the whole network, or what you can do, you can freeze this pre-trained backbone and just from here freeze this part and just train it. Okay, so it's up to you, any way you can try, but what I think the preferred way should be, see, just freeze out this above part and train them for few epochs. Okay, so that they also have some weight, then again train the complete network. That would be, I think, the best strategy. If you have any comment on this training strategy, then please give it below. We'll see and I'll discuss them, or maybe I can use it in next video. So now we'll move on to the training part. So now we'll start writing the code for the training part. So first of all, we are going to import the required libraries, functions, etc., which we require at the top. So first is this OS module. So here we're going to create some folders, we're going to save some file, we need paths. So that is why we use OS, just to make sure there's dependability between OS, rather this should code should run on different OS, because like especially in Windows and Ubuntu, there's a difference between slashes. Like I think Ubuntu Linux use this slash and Windows use this. So this small difference just stops your code from working properly. So if you're a Windows guy, always check your path first. Okay, this is the one of the most common mistake that ever happened. Okay, next is a numpy, because we are dealing with images. When you read image using OpenCV, they are read as numpy. That is why we require these two. And then we're going to use pandas to read all our CSV file. Then we have glob if we require to extract any files, a set of files from folder, we're going to use this. After that we have TensorFlow. So from TensorFlow we have imported those callbacks, the optimizer. Next we have train test split function from sklearn.model selection. This train test split function would helps to split the train data into two parts, training and validation. I think 80-20 we split we're going to use. And next we have imported our architecture, which we have built here. See, okay, so we are done with import part. Now we're going to define some global parameter. So global parameter basically means these variables are globally defined so that anyone, any function or class can easily use them. Okay, okay, next we're going to define a function called create dir. It's going to take the path first. So in this function, first of all, we're going to check if that path exists or not. If not, then create that path. If not, os.path.exist, and if not, then os.make dirs path. Now we'll move on to the main statement, that is if name equals to main. So this is where the execution of the Python program begins. So let's see if you have this line, this is from where the execution begin, and if you don't have this line, then it would check from the starting and start executing in that sequence. So I feel it's better to write this line. Like I don't even remember what I call. I usually call this the main function or main line. If anybody knows, then please write it down below. Okay, so we'll seed the environment first. Like seeding is like important thing when you're working with deep learning, because the weights of the architecture are randomly initialized. Let's say I train without seeding, you train without seeding, so it would be different random number every time. So just to make sure we have reproducibility in both training and testing, we try to seed the environment. Seeding helps to make sure we generate same random number every time. Like this is a simple explanation I can give. I seed these two libraries. If there's any other library which you want to seed, you can write its code here also. Next, we're going to create a directory to save some file. Save file. So we're going to use our function create dir, a directory called files. Next, we're going to have some hyperparameters. So here we have height as 256 pixel, width 320 pixel. Then we have batch size. So batch size you can set accordingly. As I'm using a 1390 GPU, which has 24 GB of memory, like graphic card memory, not RAM. Okay. So my GPU system can support this batch size. So it may happen that your system may not support. So you can decrease or increase it accordingly. Next we have learning rate, and after that we have epoch, that is 500. So we are not going to train the model of 500 epochs. Here we are using this early stopping callback. So this callbacks helps to stop the training when there's no performance improvement. Now we're going to define some path. So first is this model path, this is basically the checkpoint or wait file, and it would be stored in the files folder with the name model.h5. Next we have our log file, which would also be stored in the files folder, and after that we have our dataset path. Now let's write the code for loading the labels. If you remember the CSV file which contain name of all the 196 classes. So let me say load labels, and we're gonna give it the dataset path. So let's define this function here. So we're gonna say def what is the name function is load labels. Okay, so it's gonna give a path. Okay, so we're gonna say df, that is data frame, pd pandas read csv. Okay, it should be small. Next we need to give path, so I'm going to use os module layer or library, you can say. First path, then names.csv. So just make sure you have proper name. Our csv file don't have any header, so we're going to say header equals to none. So we have our data frame here. Now let me print df.head. Let's print first 10 values. So let me execute. So you can see first 10 values. So this is the name. Okay, now let us extract the name. So we can say names is equals to df 0, because that now we don't have any name. So and this is the first column, so we're going to say 0, and we're going to convert it to a list for our easiness, and we're going to give back these names. Okay, so these are our classes. Okay, now we can also have number of classes, the global variable. This would be length of classes. Now let's print some class, or let's print the whole list. See, so you can see all those classes, and the length would be 196 only. Now let's print the length num classes. You can see 196. So these are the number of classes which we have. Now we're going to load the data set. Let's write a function called load data set. First of all, is going to take the data set path. Let's give classes also. Let's split 0.2. So this is the function we would create. Def load dataset path classes split 0.2. Okay, so we are in this function. So first of all, what this function would give, just I'll tell you first of all. So it would give you the training, validation, and the testing data set. Okay, these three data set it would give you back. So if you remember, we have two files in our data set. Let me show you the data set. Just wait, let me open it in my folder on the second screen. I just a bit of time. Okay, I'm here. So it should be Stanford. Where is Stanford here? So if you see, we have these two files for training and testing. So we need to write a program which would help us to read all these things, okay, much easily. Okay, so we need to extract the name, then these bounding boxes point, then this class ID. Okay, so we need a program for this also. So what we do, so let me just simply write the code first, then I'll show you. So first of all, we're going to work with our training data set. So let's we have training images, then we have training b boxes, then we have train labels, that is classes, and again we're going to write a function called load data path classes and train if train equals to true. This function would be common to both training and testing file. Okay, So let me write this code here. I know it's a bit complex, just get it easily. It will be really easy, just don't worry. Train, by default you're gonna say it's true, and if it is false, this means we are working with testing file. Okay, so these are our value which we're gonna give back, b boxes and then labels. So let me define, and so let us define empty list. Okay, so now we need to load the file. So if train equals to true, then we have a file. So we're going to read this file using pandas. So this would be our file if training is true. Else we would have a separate file. So now you can see how easily we can differentiate between training and testing based on this train variable. Now we have data file, and the structure of both the files are same, whether it is training or testing. Now we're going to index over these data frame, index row in df.iter iter rows, iterating over rows. Now first row would be, because we don't have any header names, so we're going to work with index. First would be name, after that we have x1. Now it would be integer because the value would be a string and we need to convert it into integer. Then we have y1, x2, y2, and then class label. Okay, so we have all these 6 values now. So what are we going to do? If you remember, okay, just try to remember the class index in this are from 1 to now 196, but in our system everything began in a computer. When you write code, everything began with 0. So just remember that we need to make some changes here. So let's have a label name also, that is the class name would be classes, and then label index, that is this index value -1, because here it is a list and it begins with 0. Now let's have an image. Okay, image name. So okay, so we have this name here, we have x1, y1, x2, y2, then label, then is label class. Now why do we need this label class? For the image path. I'll show you how the image path is. Let us again, so let's say your file name is this. Okay, you have this class. Now how are you going to find it? Okay, this is our 14. So it has some specific name. We're going to go inside this, then this folder, then it is for train. So we're going to go. So now, okay, let's wait. So let's say this is the class number 14. So we go inside that, and this is the specific name. So this is how we need to extract. Okay, I'll show you. Maybe you didn't get it. So I'll show you how it would. Let's say if train, if you are working with training data, image would be os.path.join, first path, then car underscore data, again the car underscore data. As we are working with train, so it would be train folder, then label name, okay, and then name. So this is how we're going to find the path for our image. And the same thing we're going to copy for test. Just instead of train, we're going to write test, and this is our path. Maybe you can even further write the code to check it. If it exists, it's fine, otherwise it's not fine. Now b box, x1, y1, x2, y2. Now what we're going to do, we're going to append these values in our list which we have defined earlier. So let me copy paste it. Okay, there's some mistake. Okay, there's just a bit mistake. Okay, this program is done. How simply you can just extract these values from the CSV and then properly embed. So we have 3 values here: images, bbox, and labels. Now one thing which I've noted, see, in the if you just open this names.file, I'll just tell you one simple mistake like which has ruined the entire program, and it will also ruin your entire program. So there's a name here, if you see, like there's a name here which have a slash, and I think I've changed that here, so you won't find it's like something x dash something xy. So like this is this slash here, okay, in one of the name. Okay, I'll write the name below in the comments. So just remove the slash. So there's one name here which has slash, and I'll, like, for now I don't remember the name of the car. Like, just remember this here, it has CSTV, so it has slash like this. Okay, so just remove that slash. Okay, I'll just point it down below in the description, so you don't have to worry about it. Okay, so now let's just focus on this program. So we have load the data. Okay, so now this program would work for both training and testing. Now what we do, we're going to split this data set. So let's say split size, integer length, train images into split. Now these are the number of images in the validation set. Now let's split it. Okay, so we have training images, valid images, train bbox, valid bbox, train label, and valid labels. And here we have used this train test split. So when you use this function, try to make sure, just make sure that all these three functions have same random state, because the sequence of these list matters. So if you change the random state, the sequence would also change and they won't be properly aligned with each other. Now what we can do, we can again use the same function, that is load data, and now this time we're gonna extract the test data, test image, test bbox, and test label. So this is our simple function which help us to load and split the data set properly. Okay, so now let me print all the values. So this function would return some values like this. It's really long, I know, really long sentence. Now let us print the length of each of them, that is training image, bbox, and label, for all the three set. Okay, there's a mistake here. It should be y2, not y3. Okay, and this mistake is done. Okay, here, and so we have checked it and we have removed that mistake. Now let's run this program again. So these are the size of the training, validation, and testing files. Okay, I think this data set is really good. It's like good for basic object detection, but is also that it is not so small. Okay, okay, so we are done with this part. Now what we need to do is we need to work upon the data pipeline. Okay, and before that, let me just get back to the slide. So now we'll understand the pre-processing part. Okay, so we normalize the image by converting its pixel in the range of -1 to +1. Okay, and that is the value, the input accepted by the MobileNet version 2. Even if you provide like original 0 to 255 or like 0 to 1, it would work, just that the performance would drop. Okay, the performance would get affected. And now next we need to learn how to normalize the bounding box. So if you remember, our bounding box's values are integer, so we need to normalize them. So there's a simple procedure to that. We want to convert those values in the range of 0 and 1. So what we do, we simply take x1 divided by the image width, because that can be the maximum value for the x-axis. Same we do for y. So we divide y1 with image height, because the maximum value of y cannot be greater than image height. And same we do for x2 and y2. So now we got norm x1, norm y1, norm x2, norm y2. Now the value of the bounding boxes points are in the range of 0 and 1. So with this normalization process, we convert the values of the bounding boxes which are integers in the 0 and 1. Now this is an example. See, if there is an image, okay, its height and width, let's assume, is 1000 by 1000. And here you can see the human face which have a point, that is top left x1, y1 is 250 by 250, and the bottom right x2, y2 is 750 by 750. So see, bounding box, its value 250 by 250 by 750 by 750. Now we are going to normalize it. Here you see, we divide all the values with 1000 because both height and width are 1000. Now here is the normalized values: 0.25, 0.25, then 0.75, 0.75, and this would be the ground truth value for our model. So model would learn to predict normalized value, and then we need to again rescale them according to the image height and width. So this, you can reverse this process by multiplying this normalized value with this height and width, so you again get back this integer. Now let's move back to the code and work on the dataset pipeline. So we're gonna write a function called read image bbox. So first would be image path, then bbox, then label index. So first let's read the image. We're gonna work on the image part because this function would be used inside the TensorFlow, so the string would be encoded. So we're gonna say path.decode. We're gonna read the image as RGB. Okay, now we need the height and width of the image. If you remember, we need to normalize them, so we're gonna save the original image height and width because these bounding boxes are for the original image height and width, not the resized one. Next we're going to resize it. Image. Now during resizing, when you work with OpenCV, first we give the width, then height. Like for a long time I was confused because I mostly use same height and width, so it does not matter the program work. But the problem occur when you have different height and width. Yet the width and height are not same, so it would matter what value you give first. So just remember, first width, then height. I know it's like it's strange. Like when you get the shape of the image, you first give height, then width, the number of channel. And when you resize, you need to first give width, then height. Now we need to normalize the image in the range of 0 and 1. So what we do, we take image subtracted by 127. Okay, 127, again mistake, 0.5, and then divided by 127.5. So this would convert it to -1 to +1. Let me comment it down here. Okay, now we're going to convert it to float 32. We're going to explicitly define its data type because later on we're going to need it. Okay, so we're done with the image part. Now comes the bounding box. So we have x1, y1, x2, y2, y2. Mistake, x1, y1, x2, y2. Okay, bbox. Like coding for a long time makes you distracted, so that's why I think I'm a bit distracted. Okay, now we need to normalize these values. So what we do, we divide these values with their height and width. Norm x1, divide it by width. So x-axis would be divided by the width of the image, and y-axis with the height. In this way we get normalized x and the y's. Now we're gonna append, not the append, put them in a list and make an array, norm bbox, and define it as float 32. Now we need to work with the label part. So let's have a list. all the zeros, and the length of the list should be equal to number of classes. So in Python, let's say you write this, okay, and when you type multiply it with any value, it get multiplied with that time. So now this label would be equal to 0 times num classes. So this is an easy thing. Now label. Now if you now just remember what I've told you. Label index. The label index in the file are from 1 to 1996, but we need to subtract them by 1. So they begin with 0. Class label is now we convert it to array. Okay, so we're gonna give these values back. This is image, norm, bbox, and the class label. Okay, so first function is done. That is reading image bounding box and the class label. This part is done. Now we need to write, I think, two more functions. First would be a parse function. This would act as the intermediary between the OpenCV, NumPy, and the TensorFlow. Because we cannot directly use OpenCV and NumPy in the TensorFlow. It does not allow that. So this function would do that for us. So we take three values here: image, bbox, and label. Now we're going to use a function which is defined in the TensorFlow called tf.numpy function. We're going to write the name of the function that we want to include in the TensorFlow. Then its input. Input would be image, bbox, and label. Now their output data type, and these are float 32. So that is why I've explicitly specified everything: float 32, float 32, float 30, because we need the correct value here. So now this function would again give back image, bbox, and label, but in a more usable way so that TensorFlow can use them. Now we need to define their shape. So it would be height, because we have resized this image, width, and number of channel, because it's RGB, would be third. Then bbox. So these would be 4, because there are 4 values in the bbox: 1, 2, 3, 4. That is x1, y1, x2, y2. It should be inside the curly braces. Next comes the label. So label would be 196 equals to number of classes. Now we're going to give these value back. First is image, bbox, and label. Now we're going to write the last function in the dataset pipeline process: images, bboxes, and labels. Now a batch size with the default value of 8. So see, in these two functions, read image, bbox, and parse, the input are individual image, bounding box, and labels, but here they are list. Okay, so we're going to say ds dataset. Here we're going to use tf.data API. I believe this is much easier to work with. If there's any other way, please do let me know. bboxes, spelling mistake. Next, what we do, we say ds equals to ds.map. Now we're going to use our parse function here. See, you cannot directly use this read image bbox here. You need to have this intermediary function in between that would work on both. Take the OpenCV NumPy function and make it usable in the TensorFlow. Then batch size, then prefetch. Prefetch is basically fetching some batches in advance. So let's say 10. I don't know what should be the proper value. I generally write 10. Okay, so don't ask me why have you write 10. This is just I write it, just that. Okay, so now we're going to build on the dataset pipeline. So let me directly copy paste this code. Now you have understand it. Now let's do one thing for once. Let's say x, that is image, bounding box, and y in train dataset. Now what I'm going to do, I'm going to print their shape, and then I'm going to break them here. Let's see if we have any error. Okay, the shape of first x, that is the first x, not the first x, this first variable x is 16, that is batch size 256, height 320, and then number of channel, and 16 batch size 4 because it's for bounding boxes, then for classification. So these are the shape and they are properly defined, no error in there. Now next we need to work upon our model. So we're going to say model equals to build model. We're going to give a height, width, because our model take the input shape. Then we're going to say model dot compile. And now just remember, here we have two inputs, not the two input, two output. Let's just go back to our architecture. You see we have two output, bbox and label. And when you have more than one output, make sure you give them proper name. That is why I've given them bbox and label as the proper name, because during loss we require those names. So first would be bbox. For bounding box we're going to use the binary cross entropy, because the value of bbox would be in the range of 0 and 1, and it's like it's using sigmoid as the output function. And for label it would be cross entropy because it's using softmax and it's for the classification. Label categorical cross entropy, and then optimizer is Adam, specifying a learning rate. So this is, now we're going to say model dot summary. Let's see if it run till now or there's any error. Error are important because they tell you what is not happening right. Okay, so everything is fine till now. So we'll just begin the training soon. So let us define our callbacks first, because callbacks are important. So we have 4 callbacks here. First is the model checkpoint. So it saves your wait file when necessary. It not only it would not save just save it. It would check your loss, especially it would check your validation loss. And if it decreases, because loss should be decreases, and that's better. So if it decreases, it's going to save your wait file. If the loss does not decrease, it won't save your wait file. Then we have another callback called reduce alarm plateau. So it's going to decrease your learning rate with a factor of 0.1. If for a continuous epoch, let's say 5, your validation loss does not decrease. Third one is CSV logger. So this saves all your training loss, validation loss, and other training values in a CSV file, so that later you can see them. You can build a graph out of them. Early stopping. So this last callback stops your training if your validation loss stop improving for a continuous of 20 epoch. So this is how all the callbacks work. So these are really important. Now last important statement, model dot fit. So first we give training data set, number of epoch, validation data set, and then callback. Now we're gonna start with this training. So let's run this code. Okay, so it's going to take a bit amount of time. You can see a bit big. So if I, okay, let me stop and run it again. This does not look good. Now again it would be a bit time consuming. Let's play with this. I should, just don't do it, brother. Stop. It doesn't make any sense. Now this is not good. This is bad. whether you are doing nothing. Hey, terminal brother, stop. Now if I cut the terminal, it would be like the memory would not be deallocated in the GPU. Okay, let me show you one more thing. Till then, let's say there's any case happen that your this thing stuck. Let's say you close the terminal. This work on Ubuntu Linux environment. Now I'll show you NVIDIA SMI. So you can see that this is the total memory. This is the used memory. So our memory does not get deallocated. So it's stuck here. You can see. So we cannot run our program. So what we do in Linux, we type sudo kill -9 and then the process ID. So with this simple process, you can deallocate the process ID. You basically kill that process, and that ID get and that memory get deallocated. You can see it directly jumps to 851 MB. Now what we can do, we can again start the training. Like in Windows, maybe you can try the task manager and kill or end that process. Okay, now we can begin the training again. Again, it would be same. Yeah, now it's fine. Otherwise, it would go da 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 da. Okay, so it won't take much time, but this is the total loss. That is the sum of, I think, bbox loss and the label loss. So bbox loss is less because it's binary cross entropy, and label loss is more because it's categorical cross entropy. So we need to let it train for some epoch. Okay, and then we're gonna work on it, work on the test program. So what I've done, I've already trained this program for some epochs because I don't want to wait for this. Okay, so I'll show you. Let's see. This is the log file. Let me show you the log file. So if you see, I've trained it for, I think, 2 times. First for 24 epoch, then again 20. So 25 plus 20, it's 45. Yeah, I've trained it nearly on 45 epoch. So if we see, the validation loss is 0.36, label loss is 0.14, and val loss. So here you can see everything. I've trained it. Now this is our train weight file, model.h5. So we're going to use this and work on the test part now. So training is done. I don't think there's anything left which I can tell you in the training. So let's move on to the testing part. So let's create a file called test.py. Now first of all, we are going to import all the libraries first, functions and all other things. Next, we're going to define some global parameters. Now next we have is calculating, because in this we have two output. First is your bounding box. So we're going to calculate the IOU for the bounding box, and for the this classification we're going to calculate the accuracy. So I'm going to define the IOU here. Okay, so this function take your true value and the predicted value for the bounding box. Then it find for x1 that's the maximum x1, then maximum y2 out of these two. Okay, the true and the predicted. Then it calculated the intersection area. Okay, then it find the true area, bbox area. Okay, now simple, intersection area divided by the union would be true area plus bbox area, and we will subtract the common area between the two, and this way we have our IOU. I'll make a separate video on IOU, so I'm not explaining you everything here. So I'll do one thing, I'll copy some part of the code because it's repeating. So first of all, we seed the environment with same random number that we have done in training. We're going to create a folder called results. Then we have path. First is the dataset path, second is the model. Then we load our weight file. Now what I'll do, I'll say model.summary just to check if this test file work or not. Okay, you can see it's working. So we are fine till now. next we need to define some hyperparameter, load the dataset. Let's do all at once. Okay, so here we have defined the hyper parameter, that is height and width. Then we have the labels, the class names, the number of classes. Next we have load the data set. So here we only require the test set, and what I've done, I've just selected first 1000 samples from the testing because it's really huge, so it would take time. So for this video demonstration we're going to use 1000 sample. So let's run the code and see if there's any error. Okay, you can see 1000 image, bounding box and class labels. Some error from Ubuntu. Now let's move on to the prediction and evaluation part. Prediction and evaluation. Comments are like really important. Now I have a habit of having these comments. So do tell me in the comments whether you have this habit or not, like writing comments. So we're going to loop over it. So first for image, true b box, then true labels in TQDM. So TQDM is basically a progress bar. Okay, so let's say when you use a for loop, so you don't know what is happening, how many iterations are done, how many are left. So in that case we use TQDM. It is basically progress bar. It shows you how many iterations are done, how many are left. Test images. So we need to give the number of iterations in this total variable. Okay, now first of all what we're gonna do, we're gonna extract the name of the image. So we say name equals to image. Okay, now I'll print the image. I'll do some more operation, but first I'll explain what is my process or trick. Let's print this image path first. So this is the path. Now see the slash. This slash would be different depending upon your operating system, especially you Windows guys. Please check this. Okay, just check the path. Then see. Now what we do, we're gonna take this slash, okay, and we're gonna split the string, this path, based on this slash. It would convert it to a list. See the list, and at the end of the list we have our name with extension. So we're gonna say -1. See 0001.png. Now again we can split it just to get the name. That would be dot, because the dots separate the name and the extension. So we can say 0. So if you have any better way for extracting name, just write it down below in the comments. Now we have extracted the name. Now we're going to read the image. So this process would be exactly same as the one we have done in the training part. So I'm just going to copy it. Now we need the bounding boxes, the true bounding boxes. So true x1, true y1, true x2, true y2. So these are not normalized. Okay, so these are not normalized. These values are not in the range of 0 and 1. It's integers. Okay. Now I'm going to move on to the prediction. So we're going to say model.predict x input verbose equals to 0. Now it's going to predict two things. First, the b box, then a label. Okay. Now let's print the shape of both of them. Okay, here you can see shape. Let's remove them. So we're going to say prid b box is equals to prid b box c0. Then we're going to say label index. So this label is basically a probability. Let me show you. Let me print the label. So it will show you the probability over 196 classes. You can see the probability. So let me just do much better. Let me round these values. Let's say 3 decimal places. Now you can better see what they mean. You can see. Now we can easily see which class has maximum probability. This is this. Now we'll find the index number of this. Do you get? And just again remember, these index number in the prediction are from 0 to 195. That total makes up to 196, but the true values are from 1 to 196. So do either way, subtract the true value or increase this label index. Got it? So this is how, this is basically probability. If you sum all these values, they sum up to 1. Okay, now we're going to say label index is equals to np dot arg max. So arg max, what it does, it give you the index of the maximum value. So let me print the label index, and then I will show you this. Just wait. Label and then label index. Now we'll see the label index and its probability. You can say label index 180 and its probability is 97. You can see 977. It's the round off. That's why it's. Now what we do, we're gonna have print labels as the blank list. We're gonna append it inside. Now because we need to compare both this predicted label and true label, so they need to be exactly same. So what we're gonna do, we're gonna plus it by 1. Okay, now we need to rescale the bounding box point. So this is simple. This is pred x1. So what we do, prediction b box 0 refers to x1, multiply it by width, then this is y1 multiply by the image height, then same thing. So we get rescaled x1 y1 x2 y2 for the prediction. Now we're going to calculate the IOU. So we have used this cal underscore IU function. We give true b box, and this b box value should be no, they should not be normalized, they should be integer value. Okay, that is why we have rescaled these points. So this should be rescaled value, and here we have predicted b boxes: pred x1, pred y1, pred x2, pred y2. Just one interesting thing, I have a lot of mouse in my house and they are playing. Okay, they're just disturbing me. Okay, now what we do, we're gonna plot the true b box and the predicted b box on the image. Plot b box on image. I need to somehow catch these mouses, otherwise they would cut a lot of wire. Very a lot of wire in my system. Okay, let's just get concentrated on this video rectangle. So here we're going to use this OpenCV function. Okay, what's the input? That is image on which we want to plot. Then here we need to do true x1. If you see true x1, then true y1. Then next true x2, true y2. Then the RGB code. So it should be blue. So 255.0, 0. Then the thickness. Okay, now we're gonna copy the same, or I can copy it and I can paste. So this is for the prediction. Now let's save it. Saving the image. name, then extension image. Okay, now let's say when the loop is done, we need to calculate the score. Okay. Okay, so this is first we calculate the mean IOU because we have stored all the IOU inside this mean underscore IOU value. So we find a mean for all the samples. Then you find the mean accuracy using this test label and the predicted labels. So let's run this program for just first. Ooh, yeah, this is a mistake. Indentation error. The Python is really interesting. You get an error if you have extra space. Okay, now I know because this true value are for 1000 and the prediction are for just one. Okay, so let's write some code before having this. So let's plot the IOU on the image also. Okay, so X, where we gonna plot this IOU? These are the X and Y point for that. Font size is 1. Let's write the code. CV2 dot put text. Where you want to put on the image? Then what text we want to put? So it should be IOU. Then IOU. And then just up to 4 decimal places we want. Next the XY, where we want the text to begin. Then some font family, I think it is, then font size. So I'll directly copy paste it here. It's just like a lot of time consuming and the video is already really long. I think it has surpassed 1 hour. Like if you guys are really watching it for 1 hour long, then I'm like really blessed that you guys have really supported me with this. Okay, so let me just, okay, so this is put on image. So what I'll do, I'll just break the loop here and we're gonna run it. Let's see if it works. So it's 1000 images. It's still gonna take some time, but we're gonna manage that time. It's just near about 1 minute it's gonna take, I think. So see, this is the advantage of loop. Now you can easily manage those seconds, but if you don't know, so sometime what happens is you close that program because you are frustrated waiting. This case does not happen if you have this TQDM library. So I hope you are like you will enjoy the second video on object detection. So in future I'll try to bring more concept like anchor boxes. Like one of the major thing which is introduced in YOLO version 2 is our anchor boxes. So after like these basic concepts are over, we'll also move on to YOLO because I'm also learning object detection. So I learn and bring videos to you. This is that. So you and I don't know much about the object detection. I'm also learning. So here if you see, mean IOU is 75 and accuracy is 72. And like a lot of people must be asking why we have used these two. Why not like I think we have a evaluation metric for object detection is mean average precision. So the simple answer is that I don't know what MEP is, mean average precision. So I am just starting with some basics and simple concept. So even I can understand and you can also understand it. So let's go back into our folder where we have all these files. Okay, you can see it's really small image, but the here you can see the blue one is the true value, the red one is the predicted value. Okay, the prediction is like really good. Okay, and like this is going well. Now what you can even do, you can also plot the name of the classes, but that would be too much of the information in the image. I think this one is nice. Okay, but I'll give you the code for plotting those class labels also. Let's just directly put them here. Why are we just waiting? So let me delete all these images from here. So what I'll do, I'll simply copy paste them. Okay, let's do it. So we plot the predicted class label and score. Not score. We are not in much of that complex. So now label index and then label true labels -1. Just remember that because true labels are from 1 to 196, so we subtract it by 1. Now let's again run this program. Now this time it should have class name also on the images, and let me show you. See, this is how it look. It's messy thing, but if you see, okay, let's see this example. IUU is 90 and that is really well. So blue is the predicted, and the blue box and the blue text is the true value, not the predicted, and the red one is predicted. So you can see the bounding box is also well, and the name of the class is also same, G Patriot SUV 2012. So for image, for some image you can see, but for some image like this, it's is you can see, but for some really small image you cannot see well. I think we are predicting really well, just that this class is a bit different, but you can see how near both the classes are. Mercedes Benz E class, and it's predicting E class, but it's S class. So you can further increase the training epochs, okay, and then you can train it again. But I think we are on the point where this video should be. We are learning some object detection skills. So again we have got the IU and accuracy. So if you have any new idea for this object detection series, then do comment it out, and I'll try to learn and put some videos onto it, because even I'm new to this concept. Okay, so it would also help me, and it would indirectly help you also to learn something new. So that's, I think, the end of this video. And if you have remained this part of this video, then thank you. And do make sure that you subscribe the channel, share this video with your friend on social media, because see, if views increase, likes increase, I do get motivated to make more videos. Okay, this is the fact that we all YouTuber want views and likes up to some extent. Okay? Like after a point it does not matter, because it's so much that you start, you don't just give much response to it, not response, you don't give much importance to it, because there's no above line, but there's a low line that you should not go below that. So again, thank you, and do check the description for the link of the code, data set, and all the other things. Have a nice day.